As you can see from the title of this video, this tutorial is about calculating percent yield. Percent yield ties very closely into stoichiometry because most often to get your percent yields, you have to know how much of a substance you were supposed to have gotten, called the theoretical yield. That requires doing a stoichiometry problem. Percent yield is a good way of measuring in some aspects how effective you are at performing a lab experiment. There are some experiments that have really high accepted percent yields. There's some that have significantly lower percent yields, and there's a multitude of reasons for that. But the closer you are to the theoretical yield, most often means the more effective you are doing your lab. So, percent yield can be found by using an equation. The percent yield equation is equal to the actual yield divided by the theoretical yield times 100. So, what are these two things? What is the actual yield? What is the theoretical yield? The actual yield can be described as the measured amount of product from an experiment. The theoretical yield is the hypothetical amount that you should get. It's the maximum amount of product that can be produced from a given reactant. The main difference between these two is how you get them. Right? The actual yield is obtained from the lab. It's a lab result. Either we will do an experiment where you go and gather something up and measure it, and you have to write down what it is, right? Or I'll have to flat out give it to you if we don't perform the lab to tell you what the result was. The theoretical yield can be obtained by doing a stoich problem. Right? Given that I know how much of a reactant I have, I can do a bracket problem that will let me calculate how much of a product I was supposed to have gotten. So we'll take a look at an example, and we'll just do one because you'll find it's pretty straightforward, that says, determine the percent yield of copper from a reaction where 1.85 grams of aluminum reacted with an excess amount of copper 2 sulfate to produce 3.70 grams of copper. So, if you take a look at the type of problem, the first thing we'll do is characterize into three types. Is it a normal stoich problem? Is it a percent yield problem? Or is it what we call a limiting reactant problem? Right? Well, is it a normal stoich problem? It could be. Is it a percent yield? Yes, right? Because you see percent yield. As soon as I see it's a percent yield problem, I jump immediately to my percent yield equation. And if I'm looking for the percent yield of copper, I need the percent of copper. The percent of copper is going to be the actual amount of Cu over the theoretical amount of Cu times 100. So as we go through and look to see what we have, we start looking at numbers. 1.85 is grams of aluminum, right? So that can't go into our equation because it's not copper. Right? The 3.70 grams is of copper. So I need to decide, is that the theoretical amount of copper, or is that the actual amount that we got? And if you take a look, that is a piece of laboratory data. That means the 3.7 grams is the actual amount. So what I need to do is I need to find the theoretical grams of copper. Well, the only other piece of information I have is that I've got 1.85 grams of aluminum. I want grams of copper. So you can see how this is shaping up to be a stoichiometry problem. I have grams of one thing, I want grams of another. I'm going to have to do a bracket problem for that to occur. So I have a question there, but now I need to figure out what is my chemical reaction. So we go up into the problem, and just like always, I underline things that look like they belong in a chemical equation. I see aluminum, I see copper 2 sulfate, I see copper. Right? Then I cross out anything that looks like it's a product, and sure enough it says to produce copper. So that means my reactants are aluminum plus copper 2 sulfate. So now I have to predict my reaction. So I take a look. Aluminum is an element. Copper 2 sulfate is a compound. Element plus a compound is always a single replacement. And then, according to what we learned last chapter, like charges should trade. So aluminum's in group 13. It usually gets a +3 charge, so it's a plus. Sulfate's a polyion. It's a -2, so it's a minus. And then copper is a transition metal, which are all positive. So it looks like aluminum wants to trade with copper. You would have to check your activity series to see if aluminum is above copper in the activity series. You would find that it is. And for the most part, those will always proceed that way. This chapter is about assessing whether you can do stoichiometry, not follow the activity series. All right? But in theory, you should still check. So when we trade those, what happens is copper ends up alone, and then we end up with aluminum sulfate. Now we would have to write and balance that equation. Aluminum is an element. Is it a Hoberfinkel? No. So it's Al plus copper 2 sulfate is a compound. Prefixes? No, which means symbols and charges and cross. Just to show you what that would look like, we'll go here. Cu plus 2, SO4 minus 2, cross and reduce. You end up with CuSO4. Over to the other side, copper is an element. Is it a Hoberfinkel? No. So you have Cu. And then lastly, aluminum sulfate, compound. Prefixes? No. So we have to do symbols and charges. Au is a +3. Sulfate's SO4 minus 2. Cross and reduce, and you will get Al2 parentheses SO4 parentheses 3. Lastly, you have to balance this equation. If I go to balance it, I have SO4 on the left and right, so it's a polyion, so I can keep it together. So I see 3 SO4s on the right. How can I get there to be 3 on the left? I will put a 3 here. That ends up giving me 3 coppers. I have 1 copper, so we'll get those to match by putting a 3 there. And then lastly, 1 aluminum here, 2 aluminums here. How can I get there to be 2? I put a 2 on this side. So the last thing we're going to do is solve our problem. So I start with what I'm given, 1.85 grams of Al, and as always, I get to moles as quickly as I can. Grams of Al to moles of Al. Anytime you're doing a grams to moles, one goes with moles, and you go to the periodic table to get grams, which would be 26.98. Once you have moles, now you're able to change identity. So we're going to get rid of moles Al, and then figure out what it is that I want. I want copper, so we go to moles of Cu. Remember, the mole-to-mole ratio are not automatically 1, so I have to look into my equation. So I find Cu, nope, CuSO4, there's Cu by itself. So I put a 3 next to that Cu, because there's a 3 there. I find Al all alone, it's here, which makes it a 2. Last but not least, I have to get to the unit that I'm looking for. I don't want moles, I want grams. So I put mole Cu on the bottom, gram Cu on top. 1 mole has 63.5, you're going to have to check if it's 5.4 or 5.5. Looks like it's 5.4 grams of copper. So now we're able to get ourselves a number for what we're looking for. 1.85 divided by 26.98 times 3 divided by 2 times 63.54. My calc says 6.53534. Right? Take a look at your sig figs. 3 here, 4 here, 4 here means 3 in my answer. So 66.535 has a number after it, so it becomes 6.54 grams copper. Now, is that my final answer? Absolutely not. What the reason was for getting this was to plug in up here. I needed that to figure out my theoretical amount of copper. So I should have gotten 6.54 grams of copper. I actually only got 3.70. So to get my percent yield, I just do that last little math problem. I divide 3.70 by 6.54 times 100. And I get 56.5749. I only get 3 sig figs, so it looks like we have 56.6% yield of the copper. And for some reactions, that would be pretty good. In, I'd say, most reactions, that wouldn't be a very impressive percent yield for what's going on. So, you can see how the regular stoichiometry that we did ties in. It gets us a number that we need for plugging into our percent yield equation. I hope this helped with any troubles you may have been having. If you're still having trouble, as always, please feel free to come in for some help.